Hello guys, welcome to Datafuse Analytics and also welcome to the second part of this knowledge distillation session. In the first part we covered what is knowledge distillation, why knowledge distillation is used, how knowledge distillation can be used to deploy your models into production. And also we saw the entire architecture diagram for knowledge distillation. In this session we will be implementing end-to-end what we have learnt in the part 1. The teacher model that we will be using in this session is BERT-based uncased fine-tuned Clink. So this model we need to compress it and we need to improve its inference time. Now this particular model was trained on Clink 150 dataset which is used for customer intent detection. So as I have already stated in the first part that we will be solving the problem of intent classification and hence we will to view few of the examples contained in this data and also class labels and intents which the text corresponds to. Now let's directly jump into implementation. I will be doing this implementation in a stepwise manner. Before starting this implementation, let's set up our runtime. So we need a GPU to train our student model, whatever the GPU is available. Let's connect our runtime to the GPU. So the first step is to create a knowledge distillation trainer. Okay. In this first step, now in order to perform this step 1, we need two parameters. First parameter is alpha and second parameter is T. This alpha parameter, it controls the relative weight of the distillation loss, and this T or the temperature parameter specifies how much probability distribution of the label should be smooth. If you are not aware of this alpha and T and all this hyperparameter, I strongly suggest you to go through part 1 and then go to implementation, that is in the current part 2. Okay. We will need a library called as transformers. We will import the training arguments from transformers library. From transformers import training arguments class. Okay. Now we will define our custom class. Let's name this custom class as knowledge distillation training arguments. Okay, and then the input would be training arguments. We will pass training arguments. We will define an init function. Okay. This arcs. We will put alpha 0.5 for now and temperature parameter as 2.0. And then the keyword arguments. Now this ARGS, it allows us to pass variable number of non-keyword arguments to a Python function, whereas this KWARGS stands for keyword arguments. The only difference from args and KWARGS is that it uses keywords and returns the values in the form of dictionary. Okay. So for those who don't know what ARGS and KWARGS means, then we will use super keyword. We will pass ARGS and KWARGS. Now this super function is often used with the init method to initialize the attribute of the parent class. Then we will define our parameter self.alpha equal to alpha and self dot temperature equal to temperature. Now let's code for a new loss function. The step 2 is let's code for new loss function. Now we will subclass trainer and overriding the compute loss method to include the knowledge distillation loss term KD. So here the new loss function means knowledge distillation loss. Let's import few packages. Import torch.nn as nn. We need code. Then import torch.nn.functional as f. And finally from transformers import trainer. Now we will create our custom class which is called as knowledge distillation trainer. Knowledge distillation trainer. Here we will define the knowledge distillation loss and training code etc. We will give trainer as input to this class. Let's define init functionality. First would be arguments, then the teacher model. Let's initialize it to none. Then finally keyword arguments. Okay. Then we will call this super keyword super dot init args and awargs like we did earlier. Then this self.teacher model equal to teacher model. Okay. Now let's define the loss functionality. So compute loss. Okay. Here we will require model, we will require inputs, we will require return outputs equal to false. This will define whether we want to return loss as well as outputs, or we have to just record, or we just have to return the outputs as loss. Okay. The first step is extracting cross entropy loss and logits from student model, and then we will extract logits from teacher model. So here outputs of student equals to model, and then we will pass inputs. Then let's compute the loss for student. So loss for student is this one, outputs of student dot loss. Then we will compute the logits. Logits of student equal to logits. Outputs of student dot logits. Okay. Now we will extract logits from teacher. So here outputs of teacher equals to self dot teacher model, the one which we are passing it to init function, self.teacher model dot logics. Okay, now we will compute the distillation loss. So now we will compute the distillation loss by softening probabilities. Okay, so let's take a variable, let's take loss FCT, and let's utilize this NN dot KL divergence. So KL divergence loss, this is an inbuilt KL divergence loss method which is in this torch.nn as NN that we have imported, and then we will pass reduction equal to batch mean. Now this reduction equal to batch mean argument in this nn.kl div loss function specifies that we average the losses over the batch dimension. So here we average the losses over the batch dimension. Okay, now let's take a variable which will store the distillation loss. So loss of Kd equal to self.arcs.temperature square into this loss of FCT. In that we will soften the probabilities of student as well as teacher. So let's first soften the probabilities of student. So f dot log softmax logits of student divided by self dot arcs dot temperature, and dimensionality is 1. Further, we will use the same functionality to soften the probabilities from teacher model. So here f dot logs dot f dot softmax logits of teacher and self dot arcs dot temperature dimensionality is 1. This will be our loss. Then let's return weighted student loss. So the final student loss is equal to self.arcs.alpha into loss of CE, that is the student loss, plus 1 minus self.arcs.alpha into loss of Kd, that is not knowledge distillation loss. Then simply return loss comma outputs of student if this is set to true. If this, else return loss. Let's run this block of code. So now we have defined the next step, that is the new loss function or knowledge distillation loss function. So we can rewrite here as knowledge distillation loss function, knowledge distillation and final loss function, and final loss function. Now we have prepared a foundation to train our student model, but the main important question is which student model will you prefer. So next step is how to choose a good student model. Okay. Now there are two techniques which I follow. The first is the student model has to be smaller than the teacher model. This will help us to reduce the latency and memory footprint. Okay. And the next point is knowledge distillation functions best when the teacher and the student are of the same model type. So Bert, Roberta can have different output embedding spaces. So we will not use Roberta as a good student model. Here the Bert and Distilbert have same output or similar output embedding space. So we will choose here Distilbert. Okay. Now if we select a model which is having different output embedding spaces, this creates issues for student to mimic the teacher, and the student will not learn from the teacher. Okay, so in this particular session, we will use Distilbert as our student model. Distilbert is a natural candidate to initialize the student since it has 40% fewer parameters and has been shown to achieve strong results on downstream tasks, and that is why I am choosing here Distilbert as our student model. So we are finalized to select Distilbert as our student model. Now we have to play with the data and load the data. Let's load the data. In order to load the data, we will require this library datasets. We will import this dataset function or datasets libraries. From datasets, import load underscore dataset. So as I have specified earlier, we will use the Clink 150 dataset, which is used to solve this problem of intent classification or intent detection. Now this dataset is used for evaluating the performance of intent classification system in the presence of out of scope queries, that is queries that do not fall in any of the system supported intent classes. Now let's load this. CLINC equal to load dataset CLINC OOS and then plus. Okay, now this plus configuration refers to the subset that contains out of scope training example. Okay, so let me give you a brief about this data by printing the actual instances which are present in this data. So let's take a variable sample. So sample, let's print an example from train. Let's print the first example of train. So the first example or first instance from the training dataset is, what expression would I use to say I love you if I were an Italian? So here the intent is 61. So these intents are provided as IDs, but we can easily get the mapping to string and vice versa by accessing the features attribute of the dataset. So intents equal to of train dot features of intent. Okay, then intent equal to intents dot int to str function sample of intent. Now let's print this intent. So this 61 intent corresponds to translate. The intent for this particular text is to translate something. Okay, so in this way we can recover the string format using this 2 lines of code. Now let's preprocess this dataset. Preprocess or tokenize the data. In order to tokenize the data, we will require this auto tokenizer to load the tokenizer. From transformers, import auto tokenizer. Okay, we will define the student checkpoint here. Student checkpoint equal to distil distilbert base, and we will choose uncased version. Okay, then student tokenizer equal to, we will use this auto tokenizer class. We will call from pre-trained functionality, and we will input student checkpoint here. Initially it will download this tokenizer vocabulary and etc. Okay, let's define a function to tokenize a text. So tokenize text, input would be batch, and it will return the tokenized form. So we will call student tokenizer object. We will pass batch of text, and we will say truncation equal to true. That's it. Okay, return return. Now let's take another variable which is called as clink tokenized, which will store the entire tokenized data. So clink tokenized equal to clink dot map, and we will pass a tokenize. We will use this map functionality, and we will pass this function name. We will say to tokenize in batches, and we don't require this column now, so remove columns equal to text. We don't require this text column now. Okay, so also we will rename the intent to label. So this clink tokenize dot rename column intent to labels. So why we are doing this is the trainer can automatically detect this particular labels or the target class. The trainer class can detect it. Now let's define our actual distillation trainer. So defining distillation trainer class. We will require few libraries. So first is the NumPy library. The second is load metric from datasets import. Load metric, and we will require the accuracy, because on validation data the metric used would be accuracy. So accuracy equal to load metric and then accuracy. Let's define a function for computing evaluation metric. The input would be the predictions. So predictions comma label is equal to pred, then predictions equal to np.argmax. Will input here predictions and then access equal to 1. This is a normal practice, and then we will return the accuracy score. So return accuracy score dot compute. Here predictions equal to predictions and reference is equal to these labels. Now that we have defined the compute matrix functionality, now the next point is to define training arguments for distillation trainer. Let's define training arguments for distillation trainer. We need to specify batch size. Let's keep the batch size now to 48 and then let's define the student checkpoint name. So the final student checkpoint name we can define as distill bird base uncase fine tuned on Clink dataset or fine tuned on Clink dataset, and this is our student model. Okay, now we will define the actual training arguments for student. So student training arguments equals to, we will use this function that is knowledge distillation training arguments or class which we created earlier. So this one, we will use this. And we have to define few parameters here. So output directory equal to, let's define this checkpoint as our output directory. Let's define an evaluation strategy. And that would be epoch. So after each and every epoch, the evaluation will be carried on validation dataset. Then let's specify number of train epochs. Let's define for now as 4. Let's say 5. Let's take a round figure. Then learning rate. Let's take 2e to the power minus 5. Then per device train batch size, that we have already defined as 48, so equal to batch size. Then we have to also define eval batch size. So here instead of train we have to write eval. Again we will specify the same batch size. Okay, then we will put alpha equal to 1 and weight decay as 0.01. Let's run this block of code. We have got one error that init got an unexpected keyword argument learning. So here instead of learning it has to be learning rate. Okay, now if you encounter this error, what you have to do is you have to import this package or you have to install this package pip install accelerate greater than or equal to 0.20.1. Okay, so this I am telling you only if you encounter this error. It will take its own sweet time to install. Now the package is installed. What I'll do is I'll again restart and run the entire thing. So restart and run all. So you need to restart the kernel after you install this particular package. If you don't restart the kernel, then the error will persist and you will get frustrated. So let's wait for some time to restart and run everything from scratch. So after restarting and running everything from scratch, the error is solved or the issue is resolved. Now let's move to the next step. We have to provide the student model with mappings between each intent and label ID. In order to do that, let's import the teacher model. From transformers, import pipeline, then this BERT checkpoint, BERT CKPT equal to, we will directly copy paste it from here. Okay, pipe equal to pipeline. The first argument is the task that we have to perform. So we have to perform text classification, and then we have to give model as input. So if you haven't learned about this pipeline functionality, I will again paste the link in I button as well as the description. You can go through that video. So here id to label equal to pipe dot model dot config dot id to label, and similarly label to id equal to pipe dot model dot config dot label to id. It will load the model after downloading. Let's wait for a few seconds for the model to get downloaded. This is the teacher model that we are downloading. Now let's initialize the student model. From transformers, import auto config. Now we have to specify how many number of labels are there. Number of labels is equal to, we can get it from this intents dot number of classes. Then we will define the student config. Student config is, we will use this auto config class. Auto config dot from pre-trained. The first parameter is student checkpoint. And then we have to pass number of labels equal to this number of labels. Then id to label, we have to pass same id to label. Then we need to pass label to id as well. Label to id equal to label to id. Let's run this block of code. Okay, so now we have defined this student config. Let's import this student checkpoint. So here import, we need this torch, and as we are doing this sequence classification, we need to import this auto model for sequence classification from transformers library. From transformers import auto model for sequence classification. Now in order to train, we need to initialize the device. So device is equal to torch dot device. So we will give the device as CUDA if the GPU is available. So if torch dot CUDA dot is available, else we will let the model train in CPU itself. Okay, then let's define a function which is called as student initialization, wherein the student will get loaded. So return, we will use this auto model for sequence classification dot from pre-trained functionality, and then we will input here student, the name of the student checkpoint, which we have already defined as Distilbert base uncased, and then we will provide the configuration. So config equal to student config, which we defined here, student config, and we will put this model to whatever device that we are dealing with here, or to device. Okay. Now let's start the actual fine tuning. Let's load entire teacher model and start fine tuning of student. So the checkpoint of teacher we have already defined here, so we will copy paste it from here. Let's say teacher checkpoint equals this, and then teacher model equal to, we will use the same functionality, auto model for sequence classification dot from pre-trained. The first parameter would be the name of the model, the second parameter is number of labels equal to number of labels, and then we will move this model to whatever device we want to train on. If you haven't downloaded this model, it will download for the first time. If you have downloaded this model earlier, then it will simply load this model. Okay, now let's start the fun part of training. Let's start training. So we will use Distilbert trainer equals to, we will use this knowledge distillation trainer class. We will use model init equal to student init functionality, then teacher model equal to teacher model, then arguments equal to student training arguments, then the training dataset would be clink underscore tokenized, and then we will import the train part of this. Similarly with eval dataset equal to clink tokenized, and then validation. Then we will define compute metrics functionality. So compute metrics equal to compute metrics, and then tokenizer equal to student tokenizer. Okay, now let's train this model. Distilbert trainer dot train. Hopefully everything goes well. Okay, we have got an error which is called as output student is not defined. Let's see. This has to be output student, OUT PUT. Okay, we got another error. Now this output student is not defined again. Okay, we have these outputs, don't have this output. Okay. there was a spelling mistake. Now again let's run this. Okay, again error. But for sequence classification object has no attribute logits. The error is coming here. This logits. Okay, we have done one silly error. First we need to give inputs to this teacher model, right? So outputs of teacher equal to self dot teacher model, and then we have to give inputs here. Then we have to compute logits of teacher. Then this outputs of teacher dot logits. Let's run this and again try to retrain this model. Okay, now that we have solved all the errors, the model is training and it is showing that to train entirely on 5 epochs, it will take about 6 minutes of time. The total number of steps are 1590. So the entire progress you can see here. So let's meet after the model is trained. We have encountered this error while training. This accuracy score is not defined. Let's try to solve this error. Accuracy score. Okay, here. So here it should be accuracy score equal to. Let's again run this 3 block of code and we will go to the training code now. Now we can see that our model has trained. The accuracy, the validation accuracy for 5th epoch is 91%, tending to 92%, 91.8%, and the validation loss is 0.77. Now let's compare the student with teacher model in terms of model size, parameters, and inference time. In order to compare teacher and student model, let's first save this teacher model and student model. So def save teacher model, teacher model dot save pretrained, and we will save it in a teacher model folder. Similarly, we will create a function to save student model. So Distilbert trainer, we will use this object Distilbert trainer to save student model. So Distilbert trainer dot save model, and in this we will give student model folder. Let's call these two functions, save teacher model and save student model. If we click on this folder, we can see 2 folders. First is of student model and the second is of teacher model, right? Now let's compare. First we will compare with respect to number of parameters, total number of parameters. So compute parameters and then model path. So model equal to, we will use auto model for sequence classification dot from pre-trained, and we will give model path then we will compute parameters. So parameters or weights is equal to model dot num underscore parameters, and we will simply return these parameters. So it will return total number of parameters from all the layers. Okay, so let's print teacher model parameters is equal to, we will call this functionality, and inside that we need to add a model path, right? So model path, what we can do is, we will go to teacher model, we can see here 3 dots, we will click on these 3 dots, we will copy path and we will paste it here. Okay, and then we will print teacher model parameters. So these are the total number of parameters from the teacher. Similarly, let's print student model parameter. Instead of teacher, we just need to mention student. So here, content teacher model, we have to write here student model. And then we will print here student model parameter. So we can see that this number is less than this number, but we want the actual percentage. So the decrease in percentage is teacher model minus student model divided by teacher model. Now we have to represent it in percentage. So decrease into 100. The number is 38.8%. So now we can see here that we have student model which is about 40% or 38.8% smaller than the teacher model. We have compared with respect to parameters. Now let's compare with respect to hard disk size, or how much MBs or GBs this particular student and teacher model is taking. So simply we can use ls functionality, and we can write here first, let's print for teacher model and then for student model. ls minus al hyphen block size equal to in MBs. Okay, here we can see that the teacher model is of 439 MB. It is consuming 439 MB in hard disk. Now let's print similarly for student model. In student model, we can see that only 269 MB hard disk space is utilized. So here we are reducing the footprint of the model. Our student model consumes less space in memory as compared with the teacher model. Now let's see how much time teacher model takes to infer and how much student model takes to infer. We will require the pipeline functionality. So here pipe equal to pipeline. The task is text classification. Let's load the model as teacher model first. And the tokenizer should be birth base uncased. What we will do is we will run 100 times for the same input. So we will take sample input equals, think of, let's say, train of text, and let's say we take the 101st example. First, let's do warm up. So for in range 10 equal to pipe text, sample input text. Then let's compute the time for 100 iterations, overall time. We will require time functionality, import time. So start time equal to time.time for in range 100 pipe in sample input. We will take a variable which is called as total teacher time equal time.time minus start, and then we will simply print it. Let's run this block of code. In order to process 100 examples, the teacher model took 24 seconds. Now let's see the same with student model. So instead of teacher, we will write here student. And the tokenizer would be Distilbert. So here total teacher time. Instead of this, we will write total student time. Let's run this block of code. The student model took 15.7 seconds to process this 100 requests, which is less than this 24 seconds. Now let's compute the decrease in time in percentage. So total time teacher minus student divided by teacher and print into 100. So we got about 34.7% reduction in time, which is huge. So that's it guys for this end-to-end implementation of knowledge distillation. Let's meet you in the next session. Thank you all. If you like this video, please comment on the video for your feedback and also subscribe to this channel. Thank you everyone.